We're going to be starting a new chapter today on logic. Now, when it comes to logic, there is a mathematical way of approaching logic as opposed to maybe what you're used to thinking of as what might be considered logic. So what we're going to be talking about today is we're going to be kind of doing an introduction into logic. We're going to talk about statements, types of statements that you can have, and how you can kind of categorize each type. So we're going to start off by saying what statements are. So a statement is a declarative sentence that is either true or false, but not both simultaneously. So for example, these two are statements. So Mount McKinley is the tallest mountain in North America. That is a declarative sentence. It is definitely either going to be true or it's going to be false. Now, if it's false, it's still a statement, it's just a false statement. Now, for our purposes, for the most part, you don't need to know if this is true or false. You just need to be able to say, well, that is definitely a statement. It's very clear. It could be true or it could be false, but not both. Here's another one, a more mathematical one. 15 minus 9 equals 10. Now, you all know that that is not true. So it's a false statement, but it is, in fact, still a statement. Okay, some examples of things that are not statements. For example, tie your shoes. Are we having fun yet? This sentence is false. Okay, so why are these not statements? Well, the first one, it's not whether it's true or false, it's simply a command. It's telling someone to do something. The second one, are we having fun yet? Why isn't this one a statement? Well, because it's in the form of a question. It's not a declarative sentence. All right, the last one. This sentence is false. Why isn't that a statement? Well, let's say this statement is, what we have here is true. Well, it's saying this sentence is false. So if it's true, that must mean it's false. But if this, well then, okay, let's think about it. What if this was a false statement? If this is a false statement, this sentence is false must mean this sentence actually has to be true, but we said it's false. So this is what we call a paradox. So it is not true and it's not false. It's kind of both simultaneously, right? But that doesn't quite make sense either. So that's what we call a paradox. Okay, now you can have statements put together, and we call that a compound statement. So if you have one or more simple statements combined with what we call logical connectives, and, or, not, if, then, etc. All right, and a component statement, these are the simple statements that make up the compound statement. So a compound statement has one or more simple statements combined together, whereas a component statement, these are going to be what the compound statement breaks down into. All right, let's take a look at these examples. We're going to decide whether each statement is compound or not. So here's the first one. George Washington was the first US president, and John Adams was his vice president. Again, we don't care if it's true or false right now, we just want to know, is the statement a compound statement? Well, can we break it down into multiple parts, which each can have either a truth or a false statement to it? So, George Washington was the first US president. That's one piece, right? Could be true or could be false. And John Adams was his vice president. Also could be true or could be false. So this one we would say is compound. All right, second one. If what you've told me is true, then we are in great peril. All right, so here we have two parts. See how it's an if and then. Those are logical connectives. So what you've told me is true. That's one component. And then the second component, we are in great peril. So this is also a compound statement. All right, third one. We drove across New Mexico toward the town with the curious name, truth, and consequences. Okay, now you see the word and in there, but don't be fooled. that looks like it's part of a name. Truth and Consequences is the name of the town. So as a whole, we drove across New Mexico toward the town with the curious name Truth and Consequences. That's all just one statement. So this is not a compound statement. So try not to just look for words like and or. You want to make sure that you're understanding the statement as being either made up of multiple parts put together, or if maybe that connective is actually just part of a name, for example, in this one. All right, the last one. The money is not there. Now this one's a little bit tricky. So before we were putting things into separate parts, into breaking them down into components to see if we could do that, and if we could, it was a compound statement. Now in this one, there is a logical connective, and that logical connective is not. Now this one's a little bit strange, but anytime you see something is not, or something that negates the statement, we would actually say this is a compound statement. Okay, we would say that the simpler component statement is just the money is there. Okay, so this one's a little bit different from the others. So you're looking out for negations. If there is a negation, then it is going to be a compound statement, and the component statement is without the negation. Okay, so going off that, let's go ahead and talk about negations. So the negation of a true statement is false, and the negation of a false statement is true. All right, so let's go ahead and try to come up with the negations of each of the following statements in example 2. So give the negation of each statement. First one, California is the most populous state in the country. Okay, so the negation is simply California is not the most populous state in the country. Okay, and then the next one, it is not raining today. So this one's already negated. So the negation of something that's already negated is simply taking the negation out, right? So it is not raining today. The negation would be it is raining today. Okay, let's look at some negations of mathematical statements. So we have x is greater than 11. Okay, so the negation of this would be what? Well, we want everything that's not greater than 11. So you'd think, okay, x is less than 11, but what about 11 itself? Can it equal 11 as the negation? Yes. So the negation of this is x is less than or equal to 11. All right, for the next one, 4x plus 9y is less than or equal to 36. Okay, so now we're going to do kind of the opposite of what we just did in the first one. So this statement says that it could be less than or equal to 36. So the negation must be, it must be greater than 36. Okay, there's no need to move anything around. All you have to do is look at the inequality and see how you can change that so it's the exact opposite. So really it's just change it from less than to greater than, or greater than to less than, and then account for the equal sign. So if there was an equal sign, then get rid of it. If there isn't an equal sign, then you want to include it in the negation. All right, the next thing we're going to talk about are what we call logic symbols. So rather than writing out a lot of things, we want to be able to write statements out in a more simple way. Instead of having to write out the full sentence, for example, we can use some symbols to represent what it is that's being represented in the problem and be able to work with it that way. So statements themselves are represented with letters, typically lowercase letters. For example, P, Q, or R are very popular examples of what we would use. And then connectives, we use specific symbols for each connective. So the ones that we've seen so far, we've seen and, or, we've seen not, the negation. And we would say for and, that's what we call a conjunction, right? So this statement and this statement. And the symbol we would use is this little, kind of looks like an arrow pointing upward. I like to kind of help me remember which one is which. It kind of looks like the beginning of a capital A. So I think of that as and. For or, that's a disjunction, so either this statement or this statement. So the symbol we use there is going to be just the opposite of and. It's just going to be flipped upside down, so it looks like a V. And then not, the negation, is represented with this little squiggly line, this little tilde. Okay, so let's do some problems just to get used to trying to represent some statements using these logic symbols. So example 4, let H represent my backpack is heavy and R represent it's going to rain. Write each symbolic statement in words. Okay, so the first one, we're told, okay, so H represents my backpack is heavy, so we need that part. R represents it's going to rain, okay? And then the little symbol in between them, the one that looks like the beginning of a capital A, is going to be and. So to write this out, we would say, my backpack is heavy and it's going to rain. All right, the second one, so we see the little tilde, which means we have to negate the H statement. So my backpack is not heavy. And then the symbol in between is or. So this is going to be my backpack is not heavy or it's going to rain. Okay, for this next one, you see how the entire thing is in parentheses with a negation in front. So anytime you have something like this, it's easiest to deal with the negation in front of a parentheses if you write it's not the case that, and then write whatever's in the parentheses. So in this case, inside the parentheses, we have H or R, so inside it would be my backpack is heavy or it's going to rain. Now we have the negation in front, so we can just write this as it is not the case that either my backpack is heavy or it's going to rain. We can do something similar for that last one. So we'll start off with it is not the case that, and then we'll write down what's inside the parentheses. That would be my backpack is heavy and it's going to rain. Okay, so we've talked a lot about statements. We've talked about how to represent statements using logic symbols. But now we want to talk more about, well, what if the statement is true or false? How do we know if something is true or false? All of that. And so that's where the logic part actually comes into play. And it's actually is important whether or not something is true or false, and help us draw some sort of a conclusion. So in order to help us organize all this information about whether something's true or false, we use what we call truth tables. So truth tables are tables that show all possible combinations of truth values for the component statements and the corresponding truth value of the compound statement. So basically, if you have two component statements and we want to determine, well, what if you don't know whether it's true or false? We want to know what all the possibilities are for that compound statement. Now, we have specific truth tables for each specific logical connective. And so we'll talk about 3 of them today. We'll talk about the truth table for negation, for conjunction, and for disjunction. So let's go ahead and start with negation. So for negation, there's only one statement, so let's call it P, and the negation would be not P. So in this first column here, we want to come up with all the different possibilities for P. Well, P could be true, or it could be false. And what does a negation do? Normally we read this as not P, would be the exact opposite, right? If P is true, then not P is false. If P is false, then not P is true. So negation is just the exact opposite. All right, now let's move on to a conjunction. So a conjunction involves two component statements. Let's call them P and Q. And a conjunction is when you have a statement P linked to a statement Q by the word and. So here's what we're going to write here on the right, P and Q. Now you'll notice that there are more rows in this than in negation. The reason is because we have to come up with all the different combinations of whether P is true and Q is false, or P is false, Q is true, or they're both true, or they're both false. So we have to come up with all four of those possibilities and what that makes P and Q, the compound statement. So let's go ahead and write out all those possibilities. So P and Q could be both true. P could be true and Q could be false. P is false and Q is true. And P is false and Q is false. So those are all the possible combinations of the two statements being true or false. So with a conjunction, P and Q, is that going to be true or false? Well, it depends on the component statements. For a conjunction, both statements must be true in order for P and Q as a compound statement to be true. So if you look at the first row there, both P and Q are true. So our compound statement, P and Q, is also true. Now, even if one of them is false, even if one of those component statements is false, then your conjunction, P and Q, is also going to be false. So in the second row, P is true, but Q is false, so P and Q is going to be false. All right, same with the third row. P is false, even though Q is true, so P and Q is going to be false. And then for the last one there, they are both false, so P and Q must also be false. Okay, for a disjunction, this is where we use the or connective. So again, we're going to have two component statements, P, Q, and our compound statement is P or Q. Again, on the left here, we are going to list off all the different possible combinations in terms of the statements P or Q being true or false. So this will look exactly the same as what we did for conjunction on the left. Now on the right, for a disjunction, it's P or Q. That means that as long as one of the statements is true, then the compound statement P or Q will also be true. So for that first row, if they're both true, well, then this must be true. For the second row, P is true, Q is false, but that's okay because it's as long as one of those statements is true, then your disjunction compound statement is going to be true. Same with the third row. There's at least one statement that's true, so our disjunction is true as well. And the only time in which P or Q is going to be false is if both of them are false. So these three truth tables, there will be more different logical connectives later on we'll learn about. But for now, these are the truth tables that you'll want to use to help you determine whether a statement is going to be true or false. If you see some sort of connective, you'll use this information. So the information is that for a negation, it's always going to be the opposite. For a conjunction, it's only going to be true if both of them are true. And for a disjunction, it's only going to be false if both of them are false. Let's take a look at example 5. Let P represent the statement 3 is greater than 2, Q represent 5 less than 4, and R represent 3 is less than 8. Decide whether the following statements are true or false. Okay, before we start figuring out if these are true or false, let's just right off the bat on the side, write out if P, Q, and R are true or false. So P represents the statement 3 is greater than 2. That's true. Q represents 5 is less than 4. That's false. And R represents 3 is less than 8. That's true. Okay, so let's go ahead and stick to using these, what we have here on the side here. So for this first one, we see not P and not Q. Okay, P is true, so that must mean not P is false. Q is false, so not Q must be true. Okay, now we have two statements connected by an and. So if the first statement is false and the second statement is true, well, that must mean that the logical connective, the conjunction that we have here, false and true, is going to be false. Because in order for a conjunction to be true, they both have to be true. So this is going to be false. Okay, let's look at B. We have not, and then in parentheses, P and Q. So let's deal with what's inside the parentheses first. So P and Q, so P is true, Q is false, so this is true and false. And now let's put that into the parentheses. And now let's evaluate this. True and false. Well, in order for something to be both true in a conjunction, both statements must be true. That's not the case here, so this is going to be false. But then we still have the negation out in front. So to negate a false statement, you end up with a true statement. So our answer here is true at the end. Okay, let's do one more. We have this, what looks like a very complicated statement. Because we're still using the same things for P, Q, and R, let's use that. And let's fill this in. So not P is the opposite of true, so that's false. And R, which is true. Okay. And in the second parentheses, we have not Q, so that's the opposite of false, so that's going to be true. And then not P, that's the opposite of true, so that's going to be false. All right, now let's take each parentheses at a time. So remember, anytime we see an and, a conjunction, both must be true in order for it to be true. So we have false and true, that is false. Second parentheses, we have true and false, so that is, again, false. They both must be true in order to be true. And now we have an or statement in between them. So an or statement, in order for an or statement to be true, at least one of the statements must be true. In this case, both statements are false, so false or false, this is going to be false.